Okay, so I'm happy to introduce the Dr. Elena Pinetti from the work of that. As you know, we're not a single speaker today. So she's got her PhD degree from the University of Turin and the Sorbonne University in 2021. And she has been working on particle physics, specifically in talking about the astrophysics. So today, she's going to talk about very interesting subject, purchase with cosmic order. Please.
Hi everyone, thanks for having me today. The topic that I will tackle today is how we can probe and study dark matter with cosmic voids. So we'll try to convince the cosmic voids are indeed an interesting target for dark matter searches. Now, all the results that I will show you today are already out there in the wild, in a paper whose title is "Got Plenty of Nothing, Cosmic Voids as a Probe of Particle Dark Matter." Now, a little bit about the outline of this talk. In the first part, I will give you the motivation behind this work. In particular, I will describe the gamma ray sky, which is perfect for the next talk, why it's relevant for us. Then I will introduce the cross-correlation technique, which we employed in our analysis. And towards the end, I will show you the final results. And I will describe, the halo model, how it can be extended into the halo void model. So let's start. We start by looking, and we imagine to look at the beautiful picture of the Fermilab telescope. So we look at the gamma ray sky, and we know that in the gamma ray sky, there are two main components. One is the galactic emission, where we have galactic plane, very bright galactic center with the Fermi bubbles. So this is one main component. And then we have all the resolved astrophysical sources. These are the two main components that we see in the gamma ray sky. Now, if we remove these two main components, what remains is the so-called unresolved gamma ray. Now, the unresolved gamma ray background has two particular properties. One is that it can be extragalactic, and the other is that it is nearly isotropic. And it's nearly is the key of the talk. Because we observe anisotropies in the gamma ray sky, and we really don't know what is the origin of these anisotropies. We have some ideas, but we don't know for sure. Now, why the anisotropies of the gamma ray sky are relevant for a dark matter personality? The idea is that N-body simulation and astronomical observation tell us that dark matter in the universe is distributed in a hierarchical and anisotropic way. Therefore, we expect that the electromagnetic signals that are indirectly produced by dark matter would also show a certain degree of anisotropy. So we want to understand if there is a correlation between the anisotropies that we observe in the gamma ray sky and the anisotropy that we expect from them. How can we do that? Well, one way is with the cross-correlation technique. So the cross-correlation technique, the idea is that on one side, so this is cross-correlation. On one side, we have a gravitational tracer of the matter distribution. And the gravitational tracer is telling us that matter exists and is there. It's not telling us if dark matter is a particle, it's not telling us if dark matter is a primordial black hole, it's not telling us if dark matter is modified gravity. Just telling there is a dark matter problem. On the other side, we correlate this tracer with a particle signal. For example, electromagnetic signals. It can be modified gravity, right? So if we see a positive signal in the cross-correlation between a tracer and an electromagnetic signal from dark matter, then it can be modified gravity, because modified gravity is not associated to any gamma rays. And then we can say dark matter is exotic. Now, if you look in the literature, there are many gravitational tracers that have been considered. Galaxy catalog is an example, but people have used cluster catalogs. They use H1 intensity mapping. This is like 21 centimeter line emitted by neutral hydrogen atoms. Then consider, for instance, weak lensing. In our analysis, I will show the results for an example of a galaxy catalog. In particular, we have in mind something like TAMU, which is one of the largest available galaxy catalog out there. And we also consider with lensing, and in particular, we did the forecast by thinking of Euclid, next generation detector. I have some trouble in saying next generation because now it's up there, but technically still next generation because all the data, still have to come. But these are the type of tracers that we have in mind. Electromagnetic signals, well, in principle, we don't know what the mass of the dark matter is. So in principle, one can consider gamma rays, X-rays, infrared, radio. It doesn't have to be an electromagnetic signal. You can also have neutrinos if your dark matter candidate is associated to a neutrino flux. It can be any signals associated to your dark matter candidate. But I start talking about the gamma ray sky. So this is the signal that I will focus on during the talk. So we'll consider cross correlation between gamma rays and galaxies orbitals. Now, sometimes people ask me if there is a tracer that is much better than any other, because they're all different from each other, right? And my answer is typically no, it really depends. It depends because, for example, if you look at galaxies and clusters, they have the big pro that you have a very large statistics. Because we do galaxy catalogs, we build galaxy catalogs like a long time. So we have very large statistics, but they also tend to have a kind of a drawback, which is their flux limited. You don't see a galaxy, you don't see a galaxy. Well, instead, if you look at H1 intensity mapping, you have the big pro that you're not flux limited, because you see all the light from all the galaxies. It doesn't care if you actually see the radio galaxies or not. But the problem is that it's very hard to extract the cosmological signal. So that's a drawback. If you look instead with lensing, you have the big pro that you really feel the entire matter distribution. This is what people in the literature say when a tracer is unbiased. So you really feel all the matter distribution. But if you compare, for example, the statistics of weak lensing catalog with galaxy and cluster, it's obviously like a smaller statistic. So one difference is the statistics. Yeah. Another difference are the different caveats and systematics of the analysis, how easy it is to extract the signal, for instance, but also the different systematics of each detector. Even if you do gamma rays, different gamma ray detector will have very different systematics, they will behave differently. And then another difference that will be clear later on, when later I will explain what the window function are and why they matter in our analysis, is the redshift distribution. And this will be also an important side of the story. Now, no one has asked me about electromagnetic signal with solid dark matter, because we know that maybe there is a dark matter contribution in the resolved gamma ray background, maybe observation points, but for sure we have an overwhelming astrophysical background. In particular, from the unresolved sources. So all those sources that our telescope that just not powerful enough, or maybe we're not good enough to be able to really understand and measure their contributions. And the astrophysical sources that we should care about in our analysis are of two types. One is star-forming galaxies, and the other are active galactic nuclei. And active galactic nuclei are a kind of a big family. Because when you look at active galactic nuclei, you have this central supermassive black hole, then you have the two jets. And now, if the Earth is here, so we're right in front of the jets, then we call it a blazar. And if the jet is more than 40 degrees, we will expect to us, then we call it a mesaline AGN. And blazar are typically also subdivided into categories that you maybe heard of. In the labs, we have typically a harder energy spectrum and flat spectrum radio quasar, which, as the name suggests, tends to be more radio bright. For the purpose of this talk, the only thing that we should kind of remember is that we have four types of astrophysical sources. This is kind of our enemy. And we want to understand if we can find a way to disentangle and see like a direct contribution on top of the astrophysical vector. That's our goal. And in principle, if we have patient people, just sit there and wait. They can just sit there and Fermi will see more blazars because they're very bright. And so the population that will remain would be star-forming galaxies, would be misaligned AGN, hopefully they're matter. But first, we're not patient. Second, we don't have all the time in the universe. We're human beings. So we need to find other ways. And one way is to use the cross correlation. Now, how do we estimate a cross correlation theta? With the angular power factor. Yeah. Now, we all have seen hundreds of times the angular power spectrum of CMB. The angular power spectrum is a typical tool of cosmology. People use it all the time when they do like large-scale structure. So what we do is that we take a typical tool of cosmology and we apply it in the case of particle director. Now, when people say statistical tool, it seems every time that they're trying to hide something under the cover. So I don't have, again, a lot of time, but I will try to give you a sort of very rough understanding on the physics that we can learn by looking at the angular power spectrum. So what is the, beyond the statistics, what's the physics that is included in the angular power spectrum? So let's consider a generic field. It can be density, if you want. Think of this G as a density field. You can always associate to a field, to a density field, an intensity. So we have an intensity in a certain direction. And you can always talk about intensity fluctuations. So the intensity fluctuation of your density field. Minus your average intensity. And now you can always write these in terms of spherical harmonics. Mathematically, you can do that. These are the coefficients of your expansion spherical harmonics, and these are the coefficients that enters in the definition of the angular power spectrum. The angular power spectrum is the ensemble average of the product of these two coefficients. So basically, what it's telling you is that the angular power spectrum measures the correlation between intensity fluctuations of the two observables I and j. Now, if I equal j, we call it autocorrelation. CMB, beautiful example of autocorrelation. If I differ from j, we call it cross correlation. That's what we're doing today. Now, all the definitions have something in common. They are beautiful, they are compact, and they're also useless. So this is not what people use in reality. Because what people use after pages of calculation, it's something different. So you can write the angular power spectrum. If some of you is interested, I will show you all the calculations, but not now. It's an integral over radial cumulative distance, or redshift, if you prefer, of two quantities. Window function, and I will tell more about it, times the Fourier power spectrum. So Fourier power spectrum and window functions are the two key ingredients that we need in order to bake our angular power spectrum. Now, the Fourier power spectrum measures the correlation in Fourier space. The window function instead is associated to how the observables are, how they evolve in redshift. Okay, so it's the redshift evolution. So in the next 10 minutes, I will tell you more about these two key ingredients. And we start with the Fourier power spectrum. Now, in a talk that is not about cosmic voids, at this point, the speaker would say something like, we compute the Fourier power spectrum in the halo model. And the halo model is a very useful formalism to study the large-scale structure. So the idea is very simple. We have small initial fluctuations. They grow. At the end, we have a critical density. When these density fluctuations go beyond the critical density, they collapse, a new halo form. We have the small little halos that they can merge, bigger halos that can merge. We have the bigger halos, and this is how we end up with the hierarchical structure in our universe. But this is teaching us, this very simple picture is telling us something important. It's telling us that if we look at the density fluctuation in the universe, we have an average density, and then we have the fluctuation will be something like that. When we are above a certain threshold, a halo form. So these are all the seeds that will become halos. But this means that halos do not trace the entire matter distribution. They trace just the peak in the density fluctuations. And this is what people mean when they say that they are biased. Because the bias is the link between halos, in the case of the halo bias, and the underlying matter distribution. And this will be relevant when we speak later about cosmic boils. Now, the other important thing about the halo model is that it is based on two main assumptions. And this main assumption will be kind of relaxed when it comes to cosmic boils. One assumption is that the entire matter in the universe resides within halos. And the second assumption is that we can kind of separate scales. So we can kind of study the mass distribution in two levels. One is the mass distribution inside one single halo. So it's not the small scales. And the other is the distribution, the spatial distribution of the halo themselves. Now, in this picture, you can write the Fourier power spectrum as the sum of two terms, the one halo and the two halo. Now, the one halo term measures correlation between points inside one single halo, so small scales, while the two halo measures correlation in two distinct voids. So this is more larger scales. Now, there are a lot of functions that are kind of under the carpet because all these, the one halo and two halo, depends on, one is the bias, it depends on the density profile, which is how the matter is distributed inside halos. That depends on the halo mass function, which is the number of halos per unit of mass. I don't have the time to go over this. In the case of the astrophysical sources, it's the same reasoning, one halo, two halo. But the astrophysical sources are better characterized by their luminosity as opposed to their mass. And instead of having a halo mass function, now we'll have a luminosity function. Number of gamma ray sources per unit of volume and luminosity. But the general idea and the general formalism still works. But this is a talk about cosmic boils. So there has to be something more to this. So first of all, what are cosmic boils? How do we define a cosmic boil? Now, some people might say, well, cosmic boils are empty region in the space. No, because cosmic boils are under density in the universe. So there is matter. Cosmic boils technically under matter dominate. So they're just under density. Now, the thing about cosmic boils is that we're kind of the beginning of the era of cosmic boils. So people in the past, 30 years have really done a lot of effort in studying halos, which makes sense because if you look for dark matter, you look where you expect to find a lot of dark matter, right? So a lot of effort has been done to better understand dark matter halos, but there is still a lot that we need to learn about cosmic boils. So different simulations kind of differ a lot when it comes to even important properties, but there are a few key properties where the community are slowly converging, kind of. And one is that cosmic voids on average have a density that is 10 to 20% of the average background density. The second is that cosmic voids on average are spherical, again on average. If you look at single cosmic voids, you will also find different shapes, like filaments and all stuff. And they tend to have a diameter that is 10 per megaparsec. Again, you will find some cosmic voids that is 100 megaparsec, and you will find cosmic voids that are maybe 1 megaparsec, but on average, it's order of tens of megaparsec. And the other interesting property is that matter tends to be concentrated on the boundary. If you think of halos, matter tend to cluster inside. Cosmic voids is the exact opposite. You tend to have matter that concentrates more on the outskirts. And the further away you go from the center of the cosmic voids, the more you need to approach the average background density. This kind of makes sense, right? Because cosmic voids, in a sense, are naturalized from the way that we build the dark scale structure. We have gravity that pulls matter from one place to another, and so leaves like regions under less. So it's all like very logical, if you want. But now, how in this picture, how can we extend the halo model into the halo void model? And there is a very nice paper of Voivodic et al. 2020, so it's all fairly recent, that really does this. So it goes from the halo model to the halo void model. And the idea is that in the halo model, we have a one barrier. So we say when density is above a certain threshold, a new halo forms. In the halo void model, we have a two barrier model. We say when density is below a certain density, then a new void forms. And in this scenario, we are relaxing some of the assumption of the halo model, because now we are saying that matter not only resides within the matter halos, but it also lives inside cosmic voids. And in this scenario, we can now have a proliferation of terms, because not only we have the one halo and the two halo term, but now we'll have the one void and the two void term, correlation between points inside one void, and correlation between points in two distinct voids. And you also have the crossover. In principle, you can have one particle in a void and one particle in a halo. But this is great because you have like a very nice and clean formalism that helps you separate the different components. Separate, at least theoretically, like the contribution to the power spectrum you expect from halos, and you expect from voids, and you expect from the cross. Now, in the halo void model, all this function exists for voids. Because now you will have a void bias, you have a void density profile, you will have a void mass function. Voids tend to be better characterized by their radius rather than their mass. So they will all be given in terms of radius, but who cares? Now, for the sake of time, I can't like describe each one of these functions, but there is one that I like to describe because I find this kind of puzzling and interesting. And this is the density profile. So now we'll show you density profile. So remember, like 5 minutes ago, I said when it comes to cosmic voids, there is still a lot of debate in the literature. One of the debates is on the density profile. Because from halos, there is this idea that density profile is NFW. Unless you look at the galactic center, then we can stay here and discuss if it's an Astor, Burkert, or FW. But when it comes to extragalactic, there is a sort of general consensus. There isn't such a thing with cosmic voids. So with cosmic voids, there are two main proposals. This one is the Amaus, Sutter, and Wondelt. On the vertical axis, there is the density contrast in voids. On the horizontal axis, there is the ratio between the distance from the center of the void and the characteristic diameter of the voids. So 0 is where background density and void density match the same. And here I can use one white and then the two color. So now we'll show you 3 types of density contrast for 3 different sizes. One is a small bond, relatively small bonds. So this is 9 megapars. This is -1, but we want to understand the qualitative pictures, not the numbers. Then I do green so that I match my notes. This is 30 megaparsec. And then we have this one, which is a bigger void, this would be 60 megaparsec. So the characteristic features of this profile is that smaller voids tend to be more underdense in the internal region, but they also show these compensation modes. While larger voids tend to be less underdense in the central region and kind of have no or very little compensation. Now let's see the second option. Second option is Voivodich, Lima, Rudira. Same axis. 0. So we have small voids, 9 megaparsec. Then we have kind of intermediate voids, 30 megaparsec. And then we have bigger voids, 60 megaparsec. So in this case, we have empty centers and no compensation modes. Note that all of them like kind of agree when it comes to the average density. Like the further you go, the more you need to find the background density, just for the way the raster structure is.
Yeah, can I ask a question?
Yeah.
So they come from two measurement situations.
Yeah.
So like in the centers of halos, like you typically have like resolution issues, like that you make sure that you there's some point at which you don't estimate the density correctly because the halo is not what it's called numerically. Is there like such a thing in the boundary, like in that case, in this case, like do they have like resolution issues in the boundary where they're like, is that kind of like the reason why they disagree?
So my understanding is that for cosmic voids, they use the same simulation, but the difference is in the void finders.
Void finders.
So there are like 3 different types of void finders like that you can consider. One is based on density. So what they do is that you have your simulation of your map, and you locate the minimum local density, and then you expand spheres until you reach like 10–20% of the mean background density. Then you have the Zobov algorithm, or sometimes you divide one of them. These are based on geometry. So you basically say halos and filaments naturally divide the large scale structure, and this is what so you use geometry to find voids. And the third are the so-called DIVA algorithm, dynamical identification of void analysis. This is dynamical in the sense that you think of voids as outflow region with outflow of matters. So these two use 2 different void finders.
Okay, so yeah, so I think my question was, ultimately, it making sense. Because, you're looking for like you're looking for like in the centers of halos, that's like much higher than mean density of the universe, and that's actually you're actually ending at the density.
Yeah.
Okay, that's actually your number 3 is actually kind of interesting. So you're actually looking for you actually see like you actually can plot like vector fields of particles that avoid you actually see them on flow in that. Okay.
So these are 3 very different definitions. And if you look by density geometry or outflow matters, it's very different, and that's why they differ qualitatively so much. And there are other things, like certain they say that 50% of the universe, the volume of the universe is voids, other tells is 90. So there is like a lot of like uncertainty. Now the good news for us is that we use them both to be agnostic, and the effect on our results is kind of negligible. But I still like to mention it because I think it's important, that people in the community knows where we are when it comes to cosmic void task structure. Now we have one catalog, so we can compare with observation, right? We have EBOS. I would expect so, because these are, I think many of the simulations are not just, some will be diameter only, but some might also include like various, by the way, but it will change, yes.
I think
it will
so,
change.
maybe the question is do like does the void size distribution I feel like fuzzy more.
Yeah. That's something that I was discussing yesterday when I was like at Rice University, like to see how this would affect. Yes, of course. Yes, it's we're discussing exactly that, like how these could change the results. And I think it's a very interesting question to ask. And I don't think that there is a big.
Yeah, I think like,
It'll change significantly with farmers.
I feel like they do. I feel like, yeah, if you properly go through like statistics of like void probability.
No, so I would expect a big difference.
Yeah.
But I mean, one needs to quantify, but my intuition would be yes, it would change. So that would be also something interesting to look, because it can tell us even more about the nature and the properties of that method. So I think that's something very interesting to look at. But we have observation, and we have the EBOS catalog. The EBOS catalog has about like 10,000 voids. But when they do, all the quality cuts that collaboration do, you go down to 1,200. So statistic is not super large. That's why, I mean, we need more data to have like a definitive answer, and we need more, simulations, more people working on it. But so far, it seems that this is the one that seems closer to the observation. Now, I always say that I like to think of this as a Chicago pizza, the English pizza, because you have like a thick crust, and in the external part, and that's your compensation wall. So it seems that it's a deep pizza, but we will know. And the cool thing is that yes, we have EBOS, but we'll have many more data. So there are so many more data from DESI, Euclid, FEREX. So in the next 5 to 10 years, there is a lot of new data that are coming out, and so we will learn a lot more about cosmic void.
So are these like this is all like relatively recent papers where they did this like void probability and stuff like that?
Yeah, I think this is 2020. This might be sooner, actually, 2013 maybe. It was like some of the first people to actually work on cosmic voids. But yeah, generally like 10 years max. And people are taking more interest now, partly because of EBOS, because now we have something more that we can compare with than simulation. And partly because there is, for example, inside Euclid, there is an entire part of the Euclid collaboration, like a subgroup that works on cosmic voids. So also like these new experiments are kind of pushing in that direction, because they can observe, and they will. So people are kind of taking interest in this direction. Cool. You have all of, yes, you have one yellow swallow.
So would this yellow void correlation, is that the continuity with the
Yeah. You can also do that. Yes. Yeah, but that would not be a Fourier perspective, that becomes like a bias. I think. But you can do that.
Can you the yellow correlation with void correlation?
You mean that you want to do? Yeah, usually I mean, usually you look at the Fourier power spectrum first, and then you look at other effects of the bias spectrum. I mean, we didn't check the bias spectrum, but yeah. But I mean, people use it like in large scale structure, use a bias spectrum. Okay, so this should be enough for the Fourier power spectrum. Now, the second ingredient that we need is the window function. Now, for the window function, I will show you. Now, the window function is related to the redshift evolution of the observation. So we have, so here we have on the y-axis window function normalized to the Hubble parameter and to the mean density as a function of redshift. We have 3 types of class of objects, right? Because we have the gravitational tracer, we have the astrophysical sources, and we have the. For the gravitational tracers, we have 2. We have 2 mass, light, and this tends to be, so this is like scored galaxies if you want, but yeah, maybe 2 mass was a better name. These 2 mass tends to be peak a very low redshift, 0.1, and you see that it's very squeezed, a low redshift. Very different from Euclid. glancing, because Euclid tend to have a broader peak around redshift 0.5, 0.7. Euclid goes up to redshift 2. And then we have the astrophysical sources. The astrophysical sources we have 4. So we have Elena, that peak around redshift 1. Here they go down, not because we don't have lasers, but because they're not like most of them will be at higher redshift because they are so bright that the closer one will kind of have resolved many of them. So we expect VLLAC to be at higher redshift. Then we have, I keep the same because I don't think I have enough color. Maybe use brown. Flux spectrum radio quasar. This is more like 25. Then we have star-forming galaxies. These are star-forming galaxies. And then we have, let's do blue. Let I keep red for them. Then we have mesaline HGN, which is more something like that. It doesn't really matter. What matters is that if you look at astrophysical sources, they tend to have a peak between redshift 0.5 and redshift 1. So it's more intermediate large redshift. Now, what about Darmester? Darmester would be something like that. Completely different. Because you tend to have like a peak and low redshift, and then quickly decays as the redshift increases. So the idea of the cross-correlation technique is that you want to exploit the different redshift behavior to disentangle the Darmester contribution from the astrophysical background. And if you have a tracer that focuses on low redshift, then in the angular polar spectrum, you have a superimposition of the two middle functions. So you can exploit this fact and kind of bring out the Darmester contribution, as opposed to have a tracer maybe at higher redshift, allow more to astrophysics, and so it would be maybe more interesting for astrophysical search. So you can use the cross-correlation technique also to do astrophysics. Just need to be very careful on the wavelength that you consider and on the tracer that you use.
So for your dark matter, I'm trying to understand what you mean by dark matter source. Are those like dark matter halos just integrated over all the halo map function? That's the thing you're playing right there. Or like...
So at this point, we are looking at Darmester decaying or annihilation, like annihilation of decaying of Darmester. So here, and now we'll say what candidate have in mind, but here you have the particle model.
There's a particle model there.
Yes, which is what I'm telling. Yeah.
Okay,
now
so
what I will. Yes. Yeah. It's already here. So in this case, I just show you the plot, but here there is the information on the particle. Like if you are considering wind for an axion, it will be here the information.
So I guess like the question is like, so I think like the galaxy, that's the source.
Yeah.
So, you know, of the ELAC, that's the source.
In our case, the source of the vector is annihilation of decay events. That's where I get gamma rays, right? Well, here will be, that's the thing with the power spectrum, I can disentangle, but here it's from a Darmester particle. It doesn't matter if the Darmester particle is inside halos or voids in case of decay. I just have to rescale the profile.
But that's everywhere in the universe, right?
No, because here I have to consider the density profile inside. If I want a realistic estimate of the signal cycle. Because from halos, so what you do is that you have in the power spectrum, you can kind of separate the contribution, right? So you will just pick like the void. So here you will have, so here you can pick the void from the power spectrum by selecting these two. In the window function, here you have the information on the spectrum, D and E, and then Darmester annihilating it to big bar, for example. But here you also have the information of the density profile. Now, the density profile inside halos is the NFW, the density profile inside the voids is a mouse pattern model. So I kind of have to use the correct one. Does it make sense? And then you will have a different estimate of your angular power spectrum, which is what I show you now, and I will show you how that differs. I see confused faces.
Sorry.
Yeah.
But why does it pick a low redshift for the voids? Is it the same? Would be similar as if you use galaxy clusters, for example, because the coordinator.
Well, it depends what galaxy cluster you use, but yes, but I wouldn't use galaxy cluster in voids because the probability to have galaxy clusters in voids, I think it's even lower than.
Yeah, there was an example for the standby.
Okay. Okay, no, that's the reason is that that's where you expect more of your matter to cluster anyway. And that's true in voids and halos. So that's why, and also the other reason that here you have a lot of resolved sources, while all the other matter today is kind of unresolved. So you still kind of expect that to be the case. So that would be, yeah, my reply is. Now in the, yeah, I will show you now the main results. And the main results are like 3 sets of angular power spectra. Each one will teach us a lesson. Now here, so the candidate have in mind is the matter particle that either decay or annihilate into PV bar. These PV bar usually do pions, and at the end of the day you have gamma rays. In the case of both annihilating and decaying dark matter, we have 100 GeV of mass and other annihilation section, or like the thermal one, or decay lifetime on the current one. So for a moment, we forget about astrophysical sources and we just want to understand how much am I losing looking into voids instead of looking into halos, because I expect to lose something because it's like it's under density versus over density. So the question is how much. So I will show you. Here you have the signal annihilation from halos. They will be something of the order of 10 minus 14. These are the units, typical units of the angular power spectrum. In the case of decaying dark matter from halos, it's a bit lower. It's like an order of magnitude, because inside the halos you have so much annihilation that this is kind of, you know, it's an overdensity. So you expect annihilating dark matter to be higher. If we look at decaying dark matter, it's kind of the opposite. You see, halos is first annihilation, second decay. In the case of cosmic voids, it will be first decay and then annihilation. The probability that 2 particles find themselves inside the void is obviously much lower. Now let's look at the relative distance, because this was just to show you the annihilation versus decay, decay versus annihilation. But what's matter is really how much we are losing, so the relative difference. And if I look at annihilating dark matter, it would be something of the order of 5 orders of magnitude. You don't do annihilating dark matter in fact. You lose too much. But if you look at decaying dark matter, here we're talking of a factor between 50 and 100. So if you want to look inside cosmic voids, then you better focus on decaying dark matter. But at this point, you should still be a little confused, because why should I look? I mean, I'm still losing a factor of 50 to 100. So now the second class of plot that I'll show you is now the ratio between the signal from dark matter and the signal from Astro. It's not just about measuring a signal. It's about being able to distinguish dark matter from Astro. So here we have one. That is when Astro and dark matter are at the same level. If I consider typical, so here we have 10 to the 27, which is the current bound string. And here let's say it's 10 to the 13, this is the second. And if I consider the signal from halos, it will be something like that. And basically almost this is the current bound, and basically always astrophysically dominated. So even if there is a dark matter signal, very hard to see. If I look inside cosmic voids, this is what I expect. For low decay lifetime, I expect like 4 orders of magnitude above. But if I look in the window that is unconstrained, which is this one, I expect to be the emitter dominated, like I expect the emitter signal to be above the background, up to 3 orders of magnitude above the current. So the reason why cosmic voids are, and intuitively we could kind of understand, is that you're basically in a background-free environment. And now the third set of plot is kind of a nice, I think, summary of the first and second letter. Yeah. This is decay. Now I'm doing decay. Well, from sure, yeah, you can be a positive person in that way. But yeah, I mean, from that perspective, we just focus then on the calendar method. That's why. Yes, I mean, we kind of. Yes, and then people say, well, but maybe you have substructures, you can still, you know, kind of save, but I don't know. We focus on the calendar. There is a difference if you do galaxies and with lensing. The with lensing signal is even like it's lower overall. So the overall cross correlation signal even inside halos is lower than with the galaxies. So now what I will show you is so you gain a lot if you look at with lensing in differences. You can win like by 3-4 orders of magnitude in the cross correlation with lensing, but you lose in overall signal even more. While if you look at the cross correlation with galaxies, you kind of expect 2 orders of magnitude. I will show you now. Yeah. So it's also like it depends also very much on the tracer that you consider. You know, there isn't a reply for it depends on the case. So here I have again CL versus L, and now I have on the left side I have the halos. In the other side I have voids. Again, CL over L. So if I look inside halos, I have a total signal that is order of 10 to the minus 11, 10 centimeters to the minus 2, 10 to the minus 1. Here I'm considering something that is 10, actually more 50 to 1,000. The total signal here is mostly dominated by the emitter, which is at the same level, similar level of star-forming galaxies and misaligned AGN. Which means that even if I see this signal, I can't tell you it's the emitter because it might just be that we haven't been so great in modeling star-forming galaxies and misaligned AGN. And here we have VLLR here. If you take a look at the signal from cosmic voids, I have something here of the order of 10 to the minus 13, where the total signal is basically the emitter. So here you have star-forming galaxies and minus 15, VLLR are minus 20. If you do the cross correlation with weak lensing, what will change is that you will have here minus 13, so it's like 2 orders of magnitude lower. And instead of having star-forming galaxies, you will have VLLR because of the window function. Because with lensing with Euclid is more a higher redshift, so you can see that you can also kind of select a different population by using this trick. But your signal will be even lower, and this the difference will be 4 orders of magnitude instead of 2. So you know, you win something and you lose something. That's life. So the point is that when we look at cosmic voids, we lose in terms of overall signal, but we have possibly something that is 7 orders of magnitude. So it's kind of above the background. So it's kind of hard to say, well, but what about the mismodeling of the star-forming galaxy? Because if the mismodeling is 2 orders of magnitude lower, then maybe we should fire some astrophysicists, because that's a lot, you know, like that's really a lot. What is the problem? So far, everything is good and nice. In our prediction, we consider Fermi, the great detector, but Fermi is not able to observe a signal that is order of 10 to the minus 13. It's not powerful enough. So at this point, the question is, are we still doing physics or are we doing math? Or in other words, can we observe such a signal with a feature detector? So we consider, we look in the literature, at that time we look at gamma 400, that propose 10 times better angular resolution, I think. In our analysis, we didn't use gamma 400, we used something that we call Fermissimo, because we're on Italian, and Fermissimo in Italian means super Fermi. This is 5 times the angular resolution, twice the exposure. if I was doing this paper today, I would consider the astroparticle telescope, but there is another detector on there called MASTER, which proposes something on that line. And the resolution, I think, better 3 to 10 times, so it's exactly kind of what we need. These make the noise lower and the signal visible, both inside halos and inside. So we need a next Fermi, and Dr. Mine built it, which, I mean, it's good because there are people that are thinking of what will be after Fermi. It's less good for me because I would like to see the signal today, not in 10 years from now, or 20, 30 years from now. So with my collaborators at this point, what we were discussing, we were doing is that we are trying to see if there is out there maybe another wavelength where we have other detectors more powerful, where we can actually already observe such a signal. So we had some, discussion. Where would we look? We do CTA and we look at TV, or we say let's go on the opposite side of the spectrum and we have radio, right? And the reason why we choose to give priority to radio is the theory and experimentally motivated reason. The theory reason is that in radio we have great, models, we have access to it. An experimental reason is that the SKA is under construction, its precursors, its pathfinders like Meerkat are already taking data, and they're focusing on the band that we want, version below 0.5. So that's why we're now in a follow-up paper. We're looking into cross-correlation with radio, hoping that with Meerkat or upcoming SKA, such a signal would be observable. You can do it, yes. Yeah, I mean, I will do all of that. Just give me time. Yeah, absolutely. Yeah, you can. Yeah, absolutely. So what I at the beginning I said the cross correlation is super subtle. That's why I love it, because you can mix different tracer, you get different answers. You can mix different signal, you get different answers. Even if you consider galaxies, you can use different galaxy catalogs. Some will be more a low redshift, some will be a high redshift. So even the same tracer is so different. And you can kind of play, games to take some population apart and select the different contributions. So now we're doing radio. Sure, next will be X-rays and all the others, infrared and so on. Yeah. So it's possible to do. Need time and yeah. Now we're looking into radio, but next we'll look at all the others. So in a few years, it will all be done. And that's all about it. That's what I wanted to say. Thank you for your attention.
So, like at the name of the halo and the void, can I do the calculation as like the void, like the halo being some kind of a tidal field? Because I think like this void is more like a expanded object or like expanded fluid in which like my halos are hitting around. When you calculate this, the beam of H, like halo and void, is that how you do, or like you just like model the void as well, like in a similar fashion as a halo?
You very much model the voice like a halo, in the sense that when you model a halo, so how does it work in the model? In the model, you have a function. The profile is telling you how matter is inside the so you have a small scale, and then you have the allows function that is telling you, okay, but how many halos would I expect of this mass? So you will have more smaller halos and less bigger halos, just because it takes longer to merge, in the hierarchical structure. In voids, you have something very similar. So you have the small scales where you have how matter is distributed inside a void. And in that case, it's mostly in the external part. But you also have a void mass function that tells you like how many voids of this size instead of this mass do I expect. So this is the type of formalism. I'm sure that you can use other description for sure. I mean, there are different ways of looking at it. In the allovoid model, that's the way that they do it. I mean, it's a choice, but yeah, you can look at in different ways. Yeah.
On the plot in the right, where is the sensitivity of Fermi? Is it orders of magnitude above?
These you can see with Fermi. It's like the two orders.
So 2 orders of magnitude.
Yeah, kind of. Even actually, it might be even, no. Well, with Clancy, actually, this I think we can do with Fermilab. But with like these two orders of magnitude lower, it's kind
Is it
of,
mostly the PSF for exposure or both?
so that's why we improve both of them. One is that also like when you look at the Android scale, because of the PSF, like you sum, at the end you do the overall signal in different scales, but if you can only see small here, and you can't really, you lose a lot of information, and we kind of need that information to observe it. So that's why, yeah. So that's why we consider something a bit bigger, but again, it's not too crazy, but it's next generation, we don't have it now. So that's why I'm looking at other detectors. But yeah, I mean, the autocorrelation have been measured before.
Yeah.
And even some cross correlation, like with galaxies. So they have observed like cross correlation with galaxies and cluster of galaxies from halos. It has been observed. Not at 5 sigma, I think it's like more of an order of 3, but it's a hint. So you can use Fermi for cross correlation, just not for cross reports. So yeah.
Quick question, have they like, when they mentioned void probability in simulations, did they do it as functional redshift? Because you can measure like halo formation as functional redshift. Did they, or is it just those equal?
Well, there is a
Sometimes they're
redshift.
like where for peaks sharply at redshift 0.
I think so, because they have the redshift information,
Okay.
so it should be.
Okay, I should
Because
get-
all the mass function, all they depends on redshift, so it should be, yeah. They have the redshift information. I would say so, yeah. Because all the function depends on that, otherwise you can like write the frequency spectrum, you can write the function. So yeah, they should have it on that.
Other questions? If not, let's end this.
Hi, Zoom people. I say hi to the Zoom people.
Oh, I didn't see.